a problem much like the type we were looking at when we finished on Friday. So imagine a tubular member of some kind, rigidly fixed on the back wall. And inside of it, with a much smaller diameter than even the inside diameter of the outer tube, is yet another one. So we have two tubes like that, concentric, or a tube with a concentric rod in it. And there's some kind of rigid cap over those. So I'll draw that as if it's out here. But it's really bonded to the top of those. So it's the cap itself is rigid, so there'll be no deformation in that. But that's sort of always been one of the idealizations we've used. And both of the structural member, both parts of that are intimately made and intimately adhered to that rigid cap that's on the outside. And then there's some kind of torsion applied to that. So if you need a side view to help, we have this tubular member now cut open in cross section with another material member down the inside, and then that cap over the outside, to which we've applied some kind of torsion. So if we use our right-hand rule, we can also draw that like that then. All right, pretty simple setup, a little more details to it. Let's say that it's 500 millimeters in length, that the inside material is steel, and the outside material is aluminum. Maybe there's room for coolant flow between the two or something. For some reason we've got it set up like that. Outside diameter is 76. Millimeters. Inside diameter of the rod on the inside is 50, and then the walls of the tube are 8. All of those in millimeters. Okay, see that well enough? Is that all right? Got the picture? A steel solid shaft inside a aluminum tube, all capped off with a rigid cap to which we apply some kind of torsion. All right, some of the material limits with which we must stay below. We have an allowable shear stress on the tube, and we need to stay under both of those. 120 megapascals for the steel, 70 for the aluminum. Other material properties: modulus of rigidity, 77 megapascals for the steel and 27 for the aluminum. No gigapascals. We struggled with that last week. I know you'd rather I let you get halfway through before I make those corrections, but let me do them now. Okay, I think that's all the pieces we've got. All right, so we need to determine the maximum applied torque. There's one torque that will drive one of the materials or the other to its limit in terms of the shear stress, and that then would be the design maximum on the applied torque. Got the picture? Take a second to get the whole drawing down. This is one of those that's statically indeterminate, because we certainly know that if we look just at the rigid cap, that it's got some applied torque in one direction, but because of its immaculate adhesion to the other two materials, they've got some amount of torsion that they're withstanding or applying to the cap. And all we know is that total torsion has got to equal some load taken by the two inner structures of this component, machine component of some kind. So statics alone is not going to help us. This is statically indeterminate. But that's okay, we're not worried, because we've got extra tools this term that allows us to finish these problems that we couldn't have finished last fall. Last fall, that's all the farther we could have gotten is to here. But what we need to do is decide what of the stuff from this term is going to be helpful to us. What do you think? You have to look at the problem to decide what of the tools from this term are going to be of use to us. What do you think? Good drawings there, not bad. It's awful quiet here Monday. John, what are you writing? You're doing something. You want to share it? We have two unknowns. How much torsion goes into each? Actually, this is three unknowns, I guess, since we don't know any one of those. We just know that the applied torques to the individual members has got to equal the total torque applied to the entire thing. So what other things can we bring to our aid from this term? We're looking at deformation, so it's going to have to be something of that. Any ideas? You're mad at me? Is that what happened? Did I ruin your weekend? You're going to make me pay for it?
Not really.
No? Chris, you're going to say something?
I forgot. Changing minds to this thing.
Well, yeah, but not really much change of length expected here. Yeah, the angle of twist is going to be the same on the two. However much one twists, the other is going to twist just as much. That again is on the assumption that whatever this cap is rigid. So we can also use the fact that whatever angle of twist we see in one, we'll see in the other. So we started to set that up. Then depends on a couple things. Of course, the load experienced by that member and the overall length. What else? Which those all those last ones are all independent of the load. The G, of course, is a material property, and L and GA are properties of the geometry of the problem as set up. So those two must be equal. Trouble is, that's we're still short because there's three unknowns. This is an independent equation, doesn't introduce any more unknowns, but we're still short one equation.
Go to the equation bag.
Go to the equation bag, equation bank. Now this is one where, since we have two materials and we know they're not going to be, well, I hope we know, I hope we have a feel that even though they have limits on the stress, they're not going to be at the same stress level at the same time, and there's going to be one situation that dominates these two. So we have to assume one of them is at the limit and then use that to calculate what the total load is, then check that for the other one, and if it's over the limit, then we know our assumption was wrong and we have to redo it the other way. So we can add that to it by bringing into it the stress limits. Just for a little bit of help here, I'll give you the two moments, polar moments, so you don't have to bother with calculating those. I see what I need to do. The steel is 2.03 times 10 to the minus 6. 2.003, 10 to the minus 6 millimeters to the fourth. Now that'd be meters. Meters to the fourth. And the aluminum is 0.064. 614. All right, all this stuff here is constants except for the two torsional loads that we're looking at. So those can all be calculated, and you can get this down to just a simple relationship between the two. It's just a proportionality constant between the two. That just slimlines things a little bit. So then what we need to do is assume one or the other is critical. Take that through the calculation until we find a load on the other one and test to determine whether or not it has exceeded the limit. So for example, maybe assume we're at the limit on the aluminum. Assume that's the shear stress. We're at the limit on the shear stress of the aluminum. Remember, these are allowable limits. So assume we're at the shear stress on the aluminum, use that then to find the load on the aluminum. Oops. So assume one or the other is critical. You don't know which. You have to take a guess. Assume that we're at this critical limit on the aluminum, 70 megapascals. Everything else is known so that we can then find the torsion expected on the aluminum that will make it critical. We can then go back and then test that if we're at the limit then on the steel as well. So once we find the aluminum torsion, we can then find the steel torsion that goes with that. We can then check to see if that's at the limit of the steel as well. So there's the bare bones plan. Sir?
One thing, is it possible you got the J aluminum and the J of steel switched?
It's possible. J of the aluminum. Yep. Let you check these things. Thanks, David. Trouble was I changed my subscripts from my notes to the board, so now they're all messed up. All right, everybody understand a bit of the game plan then, solving this problem? Joey, make a little sense? Assume the aluminum stress is critical. That's this one. Put that in here, then we can solve for the torsion on the aluminum. With that, we can then find the torsion on the steel. With that, in the same way, we can find out the shear stress on the steel then, and see if we're over this limit. If we're over this limit, then our assumption is wrong, and we have to redo this very same calculation with the opposite material being under the stress limit, at the stress limit. Don't forget that C is the outer radius. Yeah. For this part right here, all these values in here are for the aluminum. Because we're using the value for the stress limit on the aluminum. That work, Travis? Go anywhere? So that's what you're finding? Yeah. Okay, now, then that gives you a value in the stress and the steel, but then you have to also determine then for the steel what the shear stress is in the steel and compare that to this. And if we're over that, then this assumption was wrong.
So you plug
Yes.
Yeah.
This assumption for the most, for essential purposes, is our second equation, our third equation. assuming a value for one of the shear stresses, and then it serves as a second equation, a third equation. So that's the torsion in the aluminum,
Right, so then we plug that in.
if the aluminum's at its stress limit. Not quite the numbers I had, that's,
Pat my way out.
yeah, that's what I had. Yeah. Check your numbers, John. Several people are confirming mine.
37,
Well,
yeah, 36.9.
hang on, where's, what's 74? Not 74, 70.
I'm just putting a little extra just in case.
Yeah, see, no, I appreciate it. You're mimicking my style at the board.
Where did I get that from?
I don't know. From Joey?
Oh, sorry. Here. Not here.
Joey is just way, way back there, as far away as he can be.
Yeah, then you just.
There's too much flying chalk dust up here for Joe. Yeah, that's the number I had. Close to it. All right, most people are getting something like 3690 Newton meters on that. Give it to John. And then you can use that to find what it is in the steel. Then once we've got the torsion in the steel, you can find the shear stress on the steel and see if we're over the limit for the steel.
You didn't put it in. Oh. 70.
Yeah, once you get that,
Oh, we got 35.
then we get a torsion in the steel.
This is wrong.
0.004. Yeah, you got a decimal point off. The millimeters. Yeah, it's half of the 76. All right, once you find a torsion in the steel, then you can in the same way find the shear stress in the steel. Now that we've got that. And compare that number to the limit on the steel. Get that far, Travis? And oh, that's not decimal point, it's gonna be up there. Yeah, so the assumption is wrong. Is it working, Phil? got estimated load in the steel, then the dimensions for the steel, and that should give you then a shear stress based upon the assumption that we were already at the limit in the aluminum.
It's twice as much.
Yeah, using John math.
The assumption was wrong, that's what it's saying.
Yeah, but it wasn't wrong by that much. That's in your world, not in Travis, in my world. You get something?
Oh, it's the internet.
Okay, yeah, and that's passed, so good. And that tells you the assumption was wrong. Huh?
So which diameter are you going for?
Well, this would be the steel inside tube. So this number is 25 millimeters. And the J, thanks to David, we got corrected. Bill, you got something? Not yet? Chris, where'd you get?
Yeah. The shear stress of steel, find out what maximum shear stress is, compare it with the original value.
All right, so 530.
So what? Oh, okay. I said, oh, it's still not quite right. Well, but that's, hang on, that's a little different. Oh, that's for the aluminum. Yeah, so now you have to find it for the steel using equation 2, which is just the torsion and the 2 related by a bunch of constants. So you have to take this number, use it to find this number, which is the torsion in the steel. Then that's the one you use in here, because this is for the steel. Yeah.
Did you use J steel to get the 3690 or?
No, that's aluminum.
Because
Aluminum is 2.0. No, I used the 2.0.
okay.
I used the right numbers in here. And the C was the outside diameter, which is half of the 76. So that comes to be about 131, John. Right, 131.3, give or take a little bit. It doesn't really matter because that's greater than our allowable of 120, which indicates that the assumption is wrong.
So I can't take this and put this in.
No, because that's the torsional load in the aluminum.
So then when I take this.
You use equation 2
Right,
to find the torsional load in the steel.
okay.
And then that should be about this. That you use then to find the shear stress on the steel. And that we find is over the limit. The assigned limit of 120. Where that comes from, we're not saying. That's one of the givens in the problem. Agree, David, with those numbers? Coming up over there? Okay, once you determine that, then you have to assume now that the steel is critical. and redo essentially the same calculation you did there. And we know that it'll come below the shear stress for the aluminum because we assumed that was critical in the first one and went over, so we had to come down. Getting those numbers now, Chris?
I still have
Where?
which one I'm supposed to use after I
Okay, that's the torsion in the aluminum. You then use equation 2. We have the torsion in aluminum. All these others are just
do this.
geometry
TST.
things. So now we can get this. So once you have that, which should be that number over there, 3225, then you can figure out the shear stress in the aluminum. Samantha, you got this okay? This conclusion? Chris? Yeah? Joey? Phil, you up to it?
Yep.
Okay. Then it's a matter of going through the same numbers. You should get then the torsion and the steel. You have that, Tom?
I got 2.9.
Yeah, 2950, 2.9 if you use kilonewtons, kilonewton meters, or 2950. Doesn't matter which, as long as you're consistent. Then back into equation 2 to find the load in the aluminum, and then determine the shear stress in the aluminum. And we already know it'll be below this because we reduced the entire load since we first found the steel was the limiting number. So the torsion in the aluminum then is 3375, which we know is less because we had been at 3690 with our original assumption. And it's not quite the answer. The answer was what's the total load, and so it's a matter of summing all those up. Because that's what we've done now, is found the division between the two and then adding it together gives the total. So, Chris, you getting those numbers now? John, a little better? Joe, okay? Getting those? Bill? What? Where are you?
Oh, I see. So it's 120 is critical.
Yeah. Just, we had to pick one, we picked the wrong one. Of course, I did that by design, so you could see how to recognize that your assumption's wrong.
So I gotta go back and calculate through with
Yeah. The same steps we did here.
the 70.
You don't need to actually calculate the stress in the aluminum, because we already know it's below. That was these were the stresses at the aluminum limit, and we're already below those, so we don't need to recalculate the stress in the aluminum. That doesn't mean you don't want to know that number, but we don't need to check it to see if we're all right. We already know we're all right.
Does it matter if their portions are off a little?
I'm sorry?
I have 2947.
For this?
3371.
Oh, yeah, that's fine. That's just round off. Because if you went to 3 significant figures, we agreed just fine. And don't forget, we're not saying where these came from. We don't know if there's a factor of safety on those yet. We're just going through the calculations. in the real design, there's more details that need to be brought out.
So we go back to this,
Yeah. So, you're right here, know that that's over the limit for the steel. So now we go back and then assume this value, the limit value, for the steel. And essentially redo the calculation, only each of the different pieces is swap the roles. So now that we know that the steel is the limit, calculate the load in the steel using this same equation only for the steel. So now we've got that as the limit on the steel, J for the steel, C for the steel. We'll give you the load on the steel. Then in equation 2 again, now we've got the load on the steel, we can find the load on the aluminum, and we already know that's going to be below the stress limit for the aluminum because we are way below those values, not way below, quite a bit below, enough below that we know we're not at the limit of the aluminum. Chris, okay? So you should get a total load of something like 63.25. Travis, yeah? You got that? Joe, you okay?
Yeah, I get that number. Do we have to check that in the at the end like we did with the aluminum?
No,
Because we know it's not.
because being at the aluminum limit pushed us over the steel limit. So we dropped down on the steel, which is automatically going to take all the loads off to a lower level anyway, which means we're automatically below the load on the aluminum anyway. So you don't need to check it. You might need to know it for some reason, but you don't need to check it. Okay, John? Chase some of those, rest of those numbers down a little bit later. Then, because we've got a little bit more we got to get here. When you sit and just make sure you're not crossing aluminum values with steel values, and you should be okay. All right. To wrap up our look at torsion, typically in drive shafts and the like, and there's several problems of doing just that. Notice that we can also do the very same kind of thing we did with the square pieces in axial loading. That looks kind of terrible. Let's just draw it on side because it's a lot easier to draw drive shafts on the side. We can have these changes in thickness where we get stress concentrations. So depending upon what the load is and the geometry of each of these, it's no surprise, I don't think, that it depends upon the major and minor diameters of the piece, because whatever stress is felt in the large part, that same amount of stress is going to have to flow into the smaller one, causing then stress concentrations. And it also depends upon the radius of the fillet. we define it just like we did for the axial loading, where we have the stress concentration factor of some kind of allowable or maximum limit compared to the average values we have been calculating, and that's what all of these are. Remember, that assumes that we're not at any limit on the stresses, but at an average. If we look at the load levels in the piece, the real profile is something like this. It's actually quite severe, where we've been assuming that we have average stress levels. Now, if you remember, the distribution of the shear stress on torsionally loaded shafts was at a maximum at the outside and decreased linearly to the inside. But these are all average values, so our average distribution then looks something like this. It's linearly increasing from the inside to the outside, and that's what we've been using, whereas the maximum might be there. And if that's the value we need to keep below the allowable limit. So the stress concentration factor allows us to not have to miss these places of greater concern are possible. And the chart we use, it looks very, very much like that. I don't have any juice in this thing. Well, it's in your book. It's depending on which edition you have, it's 536 or 532. I'm not sure which. Yeah, for some reason the device is not.
You have one out, but I'll see if that's a necessary one. Is it necessary?
Oh, yeah, could be. That was nice of somebody to do. There we go. Okay. The table's very, very much like the one we saw for the axially loaded members. Our distribution's very much different. These tend to be kind of severe. So let's try a couple problems. So imagine we have a step shaft like that with a major diameter of 7.5 inches, minor of 3.75 inches, and a fillet radius of 9/16. Good old American values. All right. The shaft rotates at 900 RPM, and the allowable stress, that's the one that's on the upper part of the definition of the stress concentration factor, is 8 KSI. So we want to find then the maximum power output. So there's a little bit extra in here that we need to work through just to make sure we've got the parts to it. The power from a rotating loaded shaft of this kind is 2 pi f, where f is the frequency of rotation, the engineering frequency, not the angular frequency. So it's essentially this number in per seconds rather than per minute. And then whatever the torsional load is. This is the very same T we've been using as we go along here for a while. So we can take this value then, and using the allowable limit and the stress concentration factor, find then a maximum load we can put on the piece. All right, so just to help you a little bit, whether you can do it. So that's the engineering frequency, the revolutions per second, or hertz, if you will. And then that's the number we use in here. So we need to find a maximum torsion from the allowable. Once we find that, then we can calculate the maximum allowable power. Any power load over that is going to overstress the shaft. Remember this all is calculated on the smaller diameter. Because that's the part that's under the greatest stress. So the torsional load is the same in the two. And the stress is going to be a lot greater. And we need to calculate what effect the radius has on it. And we have an allowable stress. So we can figure out a stress concentration factor, use that to find the torsion that keeps us at or below that stress limit, then we can find the power. And finding K is just like it was before with the other axially loaded members, only these are torsionally loaded. It just comes right off the chart. And you can imagine in real design situations, there's a lot of these graphs. In fact, they're probably all embedded in software, design software now. Alright, so find a K, use the allowable limit to find an average stress, use that to find the torsional load, use that to find the power. So we need R over D and D over D. For this particular problem. And then those things can be adjusted as needed as you do the design iteration. Oops. (9/16) over 375. Both in inches. Of course, these little indices values are unitless, and that's the easy one. So we're at about 0.15, and we're on the 2 line, which is this second one here. So where those two hit, looks like about 1.3. Actually looks pretty close to it. Easy one to read. Remember, this is near the end of chapter 5. Now we can use that to find the average torsion, which will allow us to find the average load. Now, horsepower. Yeah.
I don't think that'll be in horsepower.
No, you put it into horsepower. Because when you go down to Ace Hardware and you're looking for a motor to connect to this shaft,
Okay.
he's gonna wanna know horsepower, because that's how they sell it down there.
Tables for that.
I mean, Earl's a bright guy, but he wants horsepower. 550 foot-pounds per horsepower.
Okay.
Okay, I don't know if I have some of the intermediate values or if I went right to the. It should all work out, but you're gonna have to move that horsepower. That's probably one unit that's gonna be with us for a very long time. If you're
Thinking
Selling
the
it.
still often will use that as a measurement of power in automobiles.
Well, no European vehicles are sold over here without mention of horsepower. What they actually have in their catalog and how they go about the design, could be that. So working out, Chris? Let's see. You have the torsion, the T before you went to the power. There. That looked, yeah, the same thing I had. Yeah. be able to get a T from that, and then once you get a T from that, you can get a power
16 would
up here.
make the situation.
And we're getting 63.7 inches.
I used to lower, at least 1.2.
Okay. Do you want to underestimate K or overestimate K?
Overestimate.
Yeah, generally. And remember, these are,
Up in this sheet.
I'm not sure even how they come up with those. I don't remember if it says in the book or not, describes how they actually come up with these charts.
Yes, verse.
Should get something like 900 horsepower,
How do you-
911.
910, is what I had, so 911 is awful close. Remembering that there's 550 foot-pounds per horsepower. Now, I can very easily make a change in the radius of the fillet if that's not enough. If 900 horsepower isn't enough, you can very easily change the radius. Would you go bigger or smaller? If you want to increase the available power output, would you go to a bigger radius or smaller radius on the fillet? So size matters, is what you're saying? Yeah, you know, without even looking at the charts, that'll just confirm it, but if you have a very, very sharp corner in there, that's an extreme stress concentration. Those areas tend to break very easily. Part of what's good about this too is that when you put these shafts together, this fillet might well be just a matter of the welding of the two shafts together. Well, if done well enough, can serve as the fillet. John, you all right? Okay, just make sure you have the intermediate value. Six times 10 to the sixth. Inch pounds is what I have to have per second. Remember, that's a power unit. Chris, you all right? No, you're not.
Inch pound per second.
Joe, did you get that? Sorta? No? You're tired too?
Tell me about it, I'm happy to.
How to get J? Oh, back here? How do you get J?
1/2 pi diameter to the 4th.
1/2 pi radius
Yeah,
to the 4th, but which radius?
small.
The smaller one. These calculations are all done on the smaller shaft because that's going to be under the greatest load.
What is that?
This 550 foot-pounds, foot-pounds per second equals horsepower.
And so we have 63.7 kips. kip inches,
Over here,
right?
yeah. And that goes in here, so that becomes units of something like, depending on where your decimal place is, inch pounds per second, because the frequency is in per seconds. The 2 pi here handles the revolution, but it's actually radians. This is actually
So then you convert.
the angular velocity.
Yeah.
Phil, all right? Get those same numbers, Samantha? Make sure that all these calculations in here are on the smaller diameter. Same thing that we did for the actually loaded stepped members.
Wouldn't the weld make it weaker? It's not solid.
Well, it depends on the quality of the weld and the material used in the weld. So yeah, it could make it weaker, but it could also make it stronger. Also possible, of course, to machine these out of one piece of material. Yeah, the science of welding, there's, you can get a master's degree, PhD on welding alone. Non-destructive testing techniques, how to check welds without taking the piece apart, which then doesn't help you any, because that really weakens it when you saw through the thing.
Yeah, but what?
So, me? No, my wife won't let me play with fire. Okay?
Fine.
All right, increasing the fillet radius to just a little bit more to 15/16 raises the power by about 11%. So then it's an engineering design decision then if that's worth it. What?
Yeah, drops your K value.
Yeah, if you increase the radius, you go up here, the K value drops, and you get more power out of it because you can put in more torsion. All right. Let's do one more and then we're done. All right, a drive shaft with a diameter change, but multiple loads on it. So 700 pound-inches back here. $500 a little bit farther along. So all of these will be in pound-inches. $300 up here. And then in the opposite direction, the only one in the opposite direction, 1,500 pounds there. All of those foot-pounds and the relevant diameters. .25 inches, 1 inch, and a fillet radius of 0.05 inches. So find the maximum expected shear stress. That's the same thing as the allowable on the definition of K factor, the stress concentration factor. make that a get out of class question. See if that'll incentivize you. So we have a shaft of 4 different loads on it, somehow. Gears are placed there, maybe even belts. Pulleys. What about the length of this? We only needed the length when we were looking at the angle of twist. Other than that, the length of any of this doesn't matter. It doesn't matter how far apart those loads are, other than that they're not right over each other. So you need to find the maximum shear stress. Maybe label the different regions. The shear stress changes in every one of those regions because the load changes. And the radius change. So you're going to need to look at it for each of these regions, A to B, B to C, C to D, and D to E. And figure out the maximum stress in each of those. Determine which is the worst case. And that's the design limit. You then decide if you have material that can take that, or you're going to have to change some of the design specifications. You're going to need to look at each of the sections. For example, A to B. We know that there's a load of 700 pound-inches. So there must be an internal torsion then of, well, the very same. So you need to do that for each of the sections to find out what the internal torsion loads are, and then figure out where the area is to worry about. This doesn't seem like too much of a worry because there's other places with greater load and smaller diameter. So the suspicion would be A to B is not going to be the limiting region. Some other region will be. So that's a pretty low load on a pretty big diameter, not of great concern.
Do we actually want to take the average, or just use the greatest one?
No, you have to look at what's happening in each section. For example, B to C, a little bit longer. We've got the 700 and 500. So you know the internal load there is 1,200 poundage. And we only do B up to C because that's one diameter. And then there's a transition at C that could be the critical point. Actually, this, the 1,200 will take you all the way to D. We have the 700 there, 500 there. Not quite up at the D load yet, so that's not on there. So there must be an internal load of 1,200.
Just take that radius down. You're switching diameters like that.
Yeah, because in the transition, there's no increase in load. The load doesn't come until down here farther. So when we're below D, not quite up at D yet, remember this section B to D, we're going until, just until we get the load in D, which is out here farther. So you have to look at a tau max in here. Well, that wouldn't be a concern because here we're at even smaller diameter.
So
But then we also have to take into account the stress concentration. Then it's probably easier to go from the other end. So. D to E. We have the 1,500 there. We're not concerned about the direction. We would be if we were looking at the angle of twist on this entire shaft, but we're not. We're just looking to make sure we're under the stress limits. So it looks like two areas of big concern. This is a large load and a small diameter. So A to B is much better off, much slower load, but a much greater diameter, so we're not even concerned with A to B. B to C is no real trouble, but we are worried about what happens at the transition. And then we're worried what happens at this, this region there, when we're down in the smaller end of the shaft, out here between D and E. So the areas of concern are that area where we have the diameter change and the stress concentration, and this area where we have the large T and the small d. We need to check both of those areas for the areas of concern. We know the other areas are not as much a concern. The loads are less and the diameters are greater.
You wouldn't have to do
Well, you should, because it's the largest load is near the end of that shaft,
in the opposite
and it's the
direction.
smallest diameter. So we want to calculate here the expected shear stress. With those loads.
So the opposite direction.
Sorry?
This is the opposite direction.
Direction doesn't matter. The only time direction matters is if we're looking at the angle of twist, where twist can be one direction and the other. This, all that matters is this magnitude. This is the internal load in that end of the shaft, which is the biggest load of any, and the smallest diameter. So it's going to be, this is a critical area you have to look at. Then so is this one where you have the area change, because that with the stress concentration factor makes things even worse. In fact, this value will be the average value you use there. Do I have that one? 4D. Or you can use that same number just with the diameter in instead of this radius. Does anybody have this one?
7640.
PSI?
Yeah.
Yep. Now, that's actually the lower number on this one, because remember the calculation, actually it wouldn't be, because we'd have 1200 in here instead. Because we're at the slightly lower load, but we have the stress concentration factor. So, we have to calculate a tau average. And then calculate a tau max from that. And since k is greater than 1, that'll be of greater concern. I don't happen to have this in the, do you have this intermediate number with 1200 in here? And using the smaller diameter,
That's 6111.
okay, now, remember that's the average and not taking into account the stress concentration factor, which we can squeeze in here, and then we're done. R over D is 0.05, D over D is what, 1.25. So, very small radius on the fillet, and the 1.25 line is this one. So, we've got a pretty high stress concentration factor. It looks like 1.58 or so, give or take a little bit. And then that gives you, multiply the 1.58 times this. That's the average shear stress in the little piece before the 300 foot-pounds is added. And so this comes out to be about 9660, which is quite a bit worse than the 7640. So the area of concern is at the step change. You might want to investigate increasing the fillet radius. If it's machined in, that's usually not too difficult a change to make. That would increase this number, bring you down to a lower K factor, and can significantly drop this number then. Phil, okay? Travis, you got those same numbers? Chris? David?
I got
Close.
1232, because I was using from D to E,
You got 1232 on here?
yeah, from D to E.
Oh, yeah. At the fillet, there's not a load of 1500. There's a load of 1200 at the fillet.
Okay, you wanted us to look at the fillet.
Well, you have to look at both. This had the greatest load on the smallest diameter, so we had to look at it, but then we also had to look back at the fillet area, even though the load was not as great.
Oh, okay.
So the area of concern is going to be right at these corners, because that's where the stress concentration factor applies.
So you only apply K where the fillet is?
Yes,
Okay.
because that's the whole point of the stress concentration factors is these area changes.
Okay.
So that's why I circled that as a region of its own and compare those two numbers.